Thanks for being here today. My name is Agnes. And these are my teammates.
I'm Raleigh Delatory.
Andrew.
I'm Gerardo.
We've been working with the UC Santa Barbara Department of Mechanical Engineering for this past week, trying to figure out how to cool devices, essentially, using MEMS technology with our mentor, Dr. Payam Bazorki, our PI, Professor Noel McDonald, and our RA, Myra Perez. So, if you're not familiar with the term MEMS, it's an acronym that stands for Micro Electromechanical System. It's a relatively new field of engineering because we've only recently been able to make things very, very small. But for some reference, imagine a human hair. Its diameter usually ranges from 50 to 100 microns, and we're working with like single microns and even smaller. So clearly we have no problem making things small, but there is another problem which we haven't been able to solve just yet. Okay, sorry. These transistors, if you embed a bunch of them on little tiny chips, you're going to have a very small area, and they're all working, they need electricity, release it as heat, and again, it's such a small area that it causes overheating problems. Okay. One thing, we've been using copper to try to cool our systems down, and so far it's working. It's kind of getting hard, but this is why we need something new.
Okay, so today's devices are getting a lot smaller and smaller, and as Agnes said, we're putting more electronic components into them, things such as higher quality speakers, higher resolution LCD screens, Wi-Fi. These are things that you all want in your devices, right? But the problem is they're getting put closer together and they're using power, which creates a lot of heat. So chips can possibly melt down or even catch on fire. That could be very hazardous to people. So the solution that we came up is to make a small cooling apparatus which we could put into these devices to help dissipate the heat.
So the MEMS device we've been working on is called a thermal ground plane, TGP for short, and it's made out of 2 titanium plates, right there. And it's important that we use titanium because it's strong, so if you drop it, it's not going to break, and it doesn't react with water. And so within the structure, we have an isolated chamber which holds water, and the water acts as a 2-phase cooling system. And so you place one end of the device over a heat source, for example a semiconductor chip, and the heat from the chip will cause the liquid water right here to vaporize. It will travel through a vapor chamber, and then the phase back to liquid, it will cool down and it will release a lot of heat, and the liquid will form in these channels down here known as the wicks, and the liquid will then transfer back to its source through these channels through capillary force, and the cycle will just continue over and over again, and it releases a lot of heat efficiently. And before you could actually have the device fully functional, you have to build it. So first you want to fabricate the 2 channels, the back plane, or the 2 plates. So you have the back plane and the wicks. And the back plane is rather simple. It's just the chamber, and the wicks is the hard part because you have to etch the channels through a chemical process. And after you have the two plates, you need to weld them together, known as packaging, and you weld them there and there. And then after you have it all welded up, you need to fill it or charge it with water through the charging ports. And keep in mind that the device is only about 800 micrometers thick, so you only need about 50th of a water drop in the device, so it's a very small amount of water.
Okay, so this is an image of one of the channels that we took with our Vigo optical 3D profiler, and as you can see, it's in 400. The channel, the length of the channel is 421 micrometers, so it's really, really small. And the red part is the channel wall. As you can see, it's like coming out, and there's about 20 of these in our TGP. So the reason we take these images is so that we can see the actual dimensions, because since it's in such a small scale, it's really easy to make mistakes. So we want our design to match our product, because it takes a lot of time and money to make these.
Here we have a titanium plate. But we actually have to fabricate it first, and we have to do it under a certain process. It's basically, we can't just have it built already and just put them together. We have to make them, and the way to make them is we have to use a process called etching. What etching is we use a strong chemical or an acid, and we actually corrode the channels through a certain process. And it'll actually look like this. Looks like we're done, or we're actually not. And the way to do this is because actually titanium is naturally a hydrophobic substance, which means that it will not attract water. And we need this because of capillary force. And capillary force is important because that's how our device works. So now what we have to do is apply a thin layer of nanostructured titanium to it. And once we put this on, it makes it hydrophilic, which is very important now. Now that it's hydrophilic, it means it loves water. Not only does it love water, but it will actually connect to the chemicals in the air. And this is a problem, because if it connects to the chemicals in the air, the water won't actually go up the channels. And here to the right we have a video that will actually prove this. But first we have to clean it. Let me explain the cleaning procedure. The cleaning procedure, you actually have to grab the device and put it under an acetone solution for 10 minutes and an isopropanol solution for 5 minutes under an ultrasonic cleaner, which shakes it really, really fast and cleans it. Then we have to dry it with a nitrogen gas gun and bake it under a heat plate for 4 minutes. And that's how you clean the device. Now let me explain the difference between a clean device and a not clean one. The one to the right is a clean one. And this actually explains capillary force to the right, because the water is going up the channels, and that's what you want to do. So we have to make it clean, and that's how you fabricate the device. Once the device is fully clean, we have to package it. And the way to package it is we actually use a laser welder, which looks like this. It pulses really, really fast and actually shoots the laser at about 6,000 degrees or so, which actually you need because titanium is very hard to work with. And you have to work with it with this type of machine. But there's a certain type of welding that you have to do first. It's called tack welding. Tack welding is important because you can't fully weld on throughout the actual points we put, because it will expand the titanium, making gaps, and you don't want gaps because later on we will make it a vacuum. And once we fully tack weld it, we fully package it. And that's basically how you weld the device.
So in order for the device to work properly, you have to fill it with the right amount of water. So we took some calculations, as mentioned before. We used the optical profiler to find the dimensions of the channels. And with those dimensions, we were able to calculate the volume of all the channels. And knowing the density of water, we found out how much mass we need to put into, mass of water we need to put into the channels to fill it all the way. If you fill it with too much water, too little water, it's not going to work properly. So rather than just going and putting that much water that we calculated in, we want to test it to see if that's right. So we put the water in the channels, filled it all up, and we realized that our calculated mass value is 50% off. We only needed about 32 milligrams of water rather than 60 milligrams. And the reason for that is because the channels are not, when you etch it, they don't form perfectly rectangular shapes. They're more oval like this. So that, therefore you have less volume and you need less water to fill the channels.
Now let's explain the experimental data. Actually, we use a copper heat pipe, and we're going to compare it to our actual device. And we can see with the actual heat pipe in our devices, let's say like an iPhone, it's about 3 millimeters thick. And the weight of it, I'm going to later explain it and compare it to our device, the TGP plane. And the copper heat pipe's actual thermal conductivity is 400 watts per meter Kelvin. And now let's compare it to our device that we made. We made it 1 millimeter in thickness. It's 6 times lighter than the copper heat pipe, and it's 10,000 watts per meter Kelvin. It's 25 times more efficient, 6 times lighter, and a lot thinner. That's what we want to show about our device.
So as Gerard just mentioned, our TGP is lighter, thinner, and more efficient than the current technology that we have, and this allows for more components on our electronic devices. So what does this mean? Something you could relate to maybe is that anyone has had an Xbox 360. When it came out in 2005, it was competing with the Sony PlayStation 3, and Microsoft wanted to do as best as they could with as many electronic components in the Xbox. But what was going on is it was overheating and the CPU was melting down and basically made it worthless, not being able to use it. So what we want to do is we want to take off that limit of overheating and put our TGPs into current devices so that we can use more components and have less risk of overheating.
So we didn't, but the research team picked titanium to create this cooling pipe because it was so good for what it needed to do. It had many of the properties we desired. It's lightweight, reacts with water well, and very hard to break. But no one had ever really thought about this before because it has very low thermal conductivity. So that's why they developed this nanostructure to help, but titanium by itself still doesn't conduct heat very well. So if we wanted to optimize this, we could possibly, or future research could possibly focus on creating a titanium alloy that had all of these properties and the added one, higher thermal conductivity. With the phase change, the process is still very efficient, but more always helps. And then we could create a better etching process, perhaps to create more uniformity in the channels. So we'd like to thank a lot of people, our mentor Payam Bazorgi, the McDonald Group, and Professor Noel C. McDonald of the Center for Science and Engineering Partnerships, CSEP, the California Nanosystems Institute, CNSI, the Jack Kent Cooke Foundation, and all of the staff we worked with at the Cooke Bridges program: Anthony, Ophelia, Jens, Jacob, Myra, Javier, Jenny, and Jason. They genuinely took an interest in us, and it's been awesome. And we want to thank everybody we haven't been able to name, but various people we've met along the way who all helped us in some way. Thank you.